on this computer. Okay, let's get this going. So last lecture, everyone. And as this is the last lecture, I'm still going to remind you that you may be recorded. If you're audible, you may be audible in the YouTube video, and if you appear, you'll appear in the YouTube video. Oh, don't fear, chat. You can always, go to YouTube. Okay, so 2 lectures today, 4 hours of content in 2 hours, right? So if I'm going a little bit quick, I am, right? So you may have to listen back to the YouTube video at half speed or something to compensate, but this will certainly require you to go home and look over the slides again, right? Because we're going to be going quite fast, and I'm not going to be able to flesh things out as much as I would like. So there's 2 lectures. The first lecture is on functional programming, and the second is on complexity and sorting. So we're going to commence with functional programming. And functional programming is actually a course that I teach in the 3rd year, Comp 3400. That's a course called Functional and Logic Programming. Now, what is functional programming? Now, at the beginning of the course, when we're talking about computers generally and programming languages generally, I said that there are at least 4 different types of programming paradigms. Imperative, which you guys know, that's the style of programming where lines are executed top to bottom, and you have things like if statements, while loops, for loops. If to the imperative paradigm you add objects, that is sort of state-based functions which can maintain state, then you get object-oriented programming. There's declarative, which is basically database programming, but the last one I said was functional programming, and I sort of glazed over it. So in particular, what is functional programming? Well, functional programming is a paradigm where functions are considered first-class objects, functions are pure, and referential transparency is enforced. Okay, that's the strict definition. So what do these words mean? Well, a first-class object means that it's expected to be allowable input to a function, right? So an integer is a first-class object, a string is a first-class object, and in fact in Python, a function is also a first-class object, but this is not sort of universal. Right, so again, a first-class object is one that can be passed easily to a function. A function without side effects means that you can't trigger state changes with your functions, right? So this means globals are out of the question. Objects are out of the question, right? Because these are all state-based type of ideas. Like a mathematical function is not context-aware. Right? You can't have the parabola be upside down on Tuesdays. Right? F of x is going to be the same f of x whenever you evaluate it, which is not the case with our functions. Our functions in Python can have a parabola which is upside down on Tuesdays, but that wouldn't be a pure function. Right? That's a function, but that's context-aware that has side effects. Okay, so no side effects, which means no globals, no objects. Finally, this notion of referential transparency is enforced. What does it mean to be referentially transparent? This essentially boils down to the statement, equal means equal. Right? There's no distinction between equality and assignment in functional languages. If you say x is equal to 2, x is 2. And what does this mean? This means that any expression can be swapped out, substituted by any other expression that's equivalent to it without affecting the program. Now that may seem like that's something that we enforce as well in Python, but that's certainly not true. Look at this statement, this basic statement of incrementing. X is equal to x plus 1. I can't substitute anything into that to maintain equality. Right? If x is 2, then I just said 2 is equal to 3. Right? So if you want to enforce referential transparency, we lose the ability to reassign variables. Right? So this is a totally different framework for programming. It's uncomfortable because not only do you lose reassignment, you lose loops. Right? So if you want to learn how to program without state changes and loops, come see me in Comp 3400. Now, I'm not really going to teach you how to program in the functional paradigm. Python is sort of what's called a semi-functional programming language. And semi-functional programming languages I really like because you sort of get the best of both worlds. Right? You get to program imperatively, which is a little bit easier, but you do get access to some of the popular functional design patterns, and I'll show you which ones those are. Okay, geez, I hope I put pauses in this. Okay, great. Okay, so the first thing I want to show you, which I wish I could have showed you at the beginning, maybe I will show the next students at the beginning, is this notion of a list comprehension. Now, I hope you guys have been shown sets at some point in your mathematical career. Is that true? You know what a set is? Okay. So if you know what a set is, you've surely been shown the set builder notation. Right? I can say, like, give me the set k squared such that k is in 0, 1, 2, 3. Right? And that generates the set 0, 1, 4, 9. I don't know why those ellipses are there. Those need to be deleted. We can also do things like, take a sum over a set. Right? So sum k over this set, k squared, and that gives you the sum 0 squared plus 1 squared, 2 squared, 3 squared, which I think is 16. We can do or write these type of statements in Python, like this. K squared for k in range 4. It's very similar to that of mathematics, like deliberately sort of an analog to what we see in math. Right? So you can always generate a list by saying, put this in the list for this in this set. Right? So k squared for k in range 4. So remember, range are the numbers 0 through 3. So k squared is going to be 0 squared, 1 squared, 2 squared, 3 squared. Right? That's how we get this. We can also say something like, give me the sum of k squared for k in range 4. And that gives you 14. Now, there's a little neat thing here. Notice how I don't have square brackets in there. So most functions which take a list and do something can also take a list comprehension, and you don't have to put the square brackets. Right? Because it would be like double brackets. It's kind of ugly. So I'm not really going to show you much else about list comprehension aside from the fact that we can use them to filter. But let's just take a look at this problem. Write a function that disassembles a string into a list of characters. Right? Should be fairly easy. Now, before list comprehension, we may have done something like this. Right? Okay, here's a function. Let's have an answer which is going to just be empty. Let's walk through the string. And let's just append every character, right? And this would work. All right, we could say disassemble A through F and get A, B, C, D, E, F. How can we do this with a list comprehension instead? Yes, sir. Exactly. All right. Instead, all I have to do is generate this list comprehension. X for x and x's. Right? Quite simple. And that indeed is going to work the same way. Right? So a lot simpler. Like, these list comprehensions are very useful. I hope you'll start using them all the time. Because it basically prevents you from using a loop. Right? And you just basically put into your list exactly what you want. I find these list comprehensions extremely clear. Okay, but there's one additional simplification we can make over this. So, like, this was just a one-line function. Like, all we did was say return this. And in fact, in Python, there's provisions for defining these one-line functions more compactly. And I think some of you have already been playing with these lambda functions. Now, in functional programming, everything boils down to a lambda function, right? It's an implementation of something called a lambda calculus. And so, again, advertisements for Comp 3400. But one-line functions like that of the previous slide can be defined using a lambda expression, which, again, is an analog to something in math. So in math, we would typically write a function like this. If we want something more complicated, we have to use sort of like case statements, but I'm sure all of you have seen something like this, like a parabola. We can define something very similar using a lambda function like this. I can say disassemble is equal to a lambda function, which is a mapping that takes x's to x for x and x's. That sort of, you have to see this, right, as the same thing as this. Right? The lambda is sort of the function definition. Right? So we can do two simplifications from that disassemble. We don't even really need to define like a function in the traditional way. We can just do it in one line. And so, in fact, this works. Perfect. Okay, one additional thing. We don't even need to give the function a name. Right? This is going to be useful for some of these higher order patterns I'm showing you. I can just say, create this function, and then evaluate it. And it will work. Right? Because this is a function, right? The thing that's in here. On the slide before, like I'm just saying this is an alias to the function, right? So the sides of this equality are sort of equivalent. So again, you don't even have to give this a name, but you can evaluate it, which is why these lambda expressions are occasionally called anonymous functions. They're anonymous because they're unnamed. Yes, sir? It's this. Yeah. Right, it's a mapping that takes everything to the left of the colon to everything to the right of the colon. Right? And yes, you can put commas to get sort of multiple inputs. But again, that's how you read this. Like, this is a function which is going to map this to this. The elements of a list comprehension may be filtered. That is, we can put an if statement into our list comprehensions to say that in order to be included in the list, you also have to satisfy like the predicate. So for example, I can create a list which is comprised of the numbers less than 100 that are divisible both by 3 and 7 in the following way. Okay, so x, these are the numbers I want in my list. For x in range 101, so again, the numbers from 0 to 100, if not x mod 3, right? So if you are divisible by 3, then x, okay, suppose x is divisible by 3, then x mod 3 is 0, which is false, and not of that is true. Right? So you have to see the thing I highlighted here is testing for divisibility by 3. I know it's sort of an odd statement. And this is testing for divisibility by 7, right? Because if you are divisible by 7, then your image mod 7 is 0, which is false, and not false is true. Okay, so this is saying x, so look at all the x's from 0 to 100, and keep them if they're both divisible by 3 and by 7. Right, and this is what you're going to get. So 21 is both divisible by 3 and 7. I actually think it's the smallest number, smallest non-zero number, both divisible by 3 and 7. And the same for the rest of them. Okay, so you can very rapidly generate lists of things. This would have been really helpful when you were doing your chess. You should revisit it. Try to refactor it with list comprehension. You'll get a staggering simplification. Okay, so here's the general pattern for a list comprehension. It's x for x in x's, right? So this is the stuff I want in the list. These are the candidates for the things in the list. And they have to satisfy this predicate. So that is to say, when px is true, x will be included. Now, it is true that actually these list comprehensions can be embedded. You can have multiple fors, multiple ifs, but don't worry about that. Right? At your level, just worry about like the one level of list comprehension. Yes, sir? Yes. Yeah, so you can, let me go here. Let me check. I'm pretty sure you can do a dictionary comprehension. Can I say x goes to a for x in range 2? Yeah. So you can do dictionary comprehensions. It's just weird because, okay, no, I suppose it would be something like this. For x in, right, so these would be your keys, right? I can say P goes to A, C goes to X goes to A. Cool. I don't think this is the best way to define a dictionary because you don't get, like you can, everything sort of has to key to the same value, right? Unless you have some type of function in there, and I don't know. I wouldn't define a dictionary like this. But you can, is the point. Okay. Okay, so that's it on list comprehensions. There is a list comprehension on your exam. Right, so there's one question I think that has a list comprehension and a lambda function. So adjust your studying schedule accordingly. Okay, so the other thing about functional programming that most functional programming languages implement is this notion of lazy computation. If I ask you to sort of do a list comprehension, the question becomes like, do you need me to do this now? Do you need me to do this later? Like, when is the absolute last instant I can perform this computation? And when a programming language sort of only computes something when that something is required, this is known as lazy computation. My whole master's degree actually was in lazy computation. So how do we support this? Well, we can't use lists anymore. What we want to swap lists out with is something called an iterator or a stream. And this is sort of like a special type of list. It has all like the features of the list, except you're not allowed to ever access an element more than once. And in fact, you have to access the elements in order. Right? So a stream is a list where you're only able to ask for the next thing out of the list. That's the only interface you have to that list. So we lose the indexing interface, and we gain this interface called next, and we're never allowed to reaccess elements. And this has a variety of advantages when you sort of are talking about program complexity or its speed. So an iterator is a stream of countable objects, right? So in order to be next, you have to be countable. Do you guys know what that means, to be countable? So like there's different types of infinities, which you may not realize. So like the counting numbers, 0, 1, 2, 3, that goes to infinity, but I can count them. Fractions, actually, like all of the rational numbers a over b, those are countable, actually. If you just imagine a grid, I can go up and down the grid. Or I can give you some method to count the fractions, right? There's always going to be what the next fraction is. The real numbers, those are infinite, but not countable. Like what number comes after 0.1? Right? So that's what's called like an uncountable infinity. So you can have an infinite list, and if that infinite list can be put in some type of order, it's called countable. And any infinite countable list can be made into a stream. Right? That's the difference here. Streams can be infinitely long. Lists can't. You can't store an infinite amount of stuff in memory. But I can create like an infinite stream, right? Because I'm only accessing one member of that list at a time. I'm not actually storing an infinite amount of stuff in memory. Right? So iterators are useful when you just need the next member of some sequence, or when you want to traverse a list exactly once, right? So next prime is a good example of this, right? So in number theory, you often just need to get the next prime, right? And it would be silly to like store the infinite amount of primes in memory and traverse that list. You just want some way of getting from one prime to the next prime. Okay, so list members are only calculated the moment they are needed. This is called delayed computation. So an object that is enumerable, which is sort of a synonym for countable, that is to say, you can put them in order. So things that can be put in order can be made iterable. That is, provide the next interface. So here's the list. A list is enumerable, obviously, because like it's in order. They're indexed. I can decorate it with this iterator sort of function, and it turns that list into an iterator. Right? So X is not a list. It's now a stream. Right? So now that it's a stream, I can start asking for what the next element is. So next axis is going to say 1. The next axis is going to say 2. The next axis is going to say 3. And after that, you get an exception, right? Saying we're done. There's nothing else in this iterator. You can't go back. That's it. We've exhausted the iterator, right? If you needed to access those things again, you'd have to like reinstantiate the iterator. But it's often the case that you don't need to access things from a list more than once. So this is fine. Strings, which are just lists, can also be iterated. This is not very surprising. Right, so next x's gives you b. I could also turn dictionaries into iterators. Right, so next x's is going to give you the key. And this is the interesting thing. When we have a for loop in Python, what it does actually is set up an iterator and just calls next. Right, so all of these nexts, this is doing the same thing that a for loop is going to do. So this is kind of neat that the for loop just says, give me anything enumerable or an iterator. I'm going to turn it into an iterator, and I'm just going to call next at each for iteration. How can we build custom iterators? Okay, there's 2 more magic methods that you need to implement in your class in order to sort of provide an iterator interface. So in order for an object to admit an iterator, you must implement the magic methods iter and next. Okay? So the iter is kind of like the initializer for your iterator. This is where you want to dump things like sort of, I want to say globals, but they're sort of like class-based globals, right? Anything that you want to remember, any type of state, like a counter. You have to return self from this iterator, right? That's obligatory. And that's sort of how it works, right? You call the iterator, it does something, and it says, here's the object again. And then you give that object to the iterator, and it spits out that object, right? So you just keep on passing it sort of the output that you just give it the input that it's output, right? It's not too hard to see how that creates an iterator. Okay, so you define sort of this initializer called iter for your iterator. You give it some state, and you return self. So the other thing then you need to do is implement next, which is just going to give you the next thing. And you don't necessarily, it could just keep returning 0 if you want. In this case, I'm just taking whatever is in counter and doubling it. Okay, so let's check this out. So my class was called foo. So here's my foo object. The foo object does not yet admit iteration. You have to sort of decorate it with iterator. You say, oh, so foo, you're my object. Can you turn into an iterator for me? And it will do so. And I'm going to call this iterator x's. And then I can just go through and say next x's is 2, next x's is 4, next x's is 8, right? You can just see that I'm doubling. And this is never going to exhaust, right? You can get an infinite number of doubles out of this. Well, until like the number's so large that it just exceeds the allowable integers by your system. You can also for loop through iterators. And you'll notice here that the iterator got reset, right? Because as I said, the for loop creates an iterator of this iterator, which kind of resets it. So keep that in mind. And this, in fact, is going to produce an infinite loop, because it's just going to keep doubling and doubling and doubling, right? So, and it's okay. It's okay that we have streams that are infinite, right? Because we're never actually going to hold the list in memory. We're only ever going to hold like, one element in memory, enough information to get the next element. Now, I've showed you iterators can exhaust. So in our custom iterators, how do we give the instruction to exhaust? Well, you just have to raise the stop iteration exception. Exceptions are a little bit different than errors. You really should avoid errors at all costs, but exceptions are kind of like, okay. I still don't like programming using these try catches, but maybe these exceptions may be an exception to that rule. So yeah, you caught that. So raise stop iteration is all you need to do when you sort of exceed some value. So I'm saying, okay, here's an iterator that's doubling. I don't want you to double beyond 10. Right? So now, if I do this, if I create an iterator, if I for loop, it's going to stop. Right? So 2 doubles to 4, 4 doubles to 8. Doubling 8 would get us 16, which is greater than 10, so we stop. Right? There's a lot of use cases for these iterators that we can't really go through because I don't have much time today, but try to think of instances where you've created a huge list where you've only ever like walked through the list once, right? That's a place where you'd want to stick an iterator. Exercise for you to do at home. Write a class that streams prime numbers. Right? Should be not too difficult. Okay, moving on. Higher order functions. So strictly speaking, a higher order function is a function that takes functions as input and returns a function as output. We've already seen this, right, in this class. I've created functions that return functions. I've created functions that take functions, right? Those are called higher order functions. In practice, higher order functions are typically those that take functions as input and return something that's not a function. And for the rest of this sort of section of the lecture, we're going to go through a bunch of standard higher order functions that are super useful, right, in functional languages, but like in any languages. You're going to see these design patterns a lot. The first of these higher ordered functions is a map. What does a map do? Well, if you give me a list and a function, perhaps I want to apply that function to every element of the list. This is called the map. Right? So mapping a function, sort of a univariate function, this is a function that takes one input and returns output, over a list x's, produces this, right? A list where the first element of that list is simply f evaluated at the first member of the list, and so on, right? That's not Python code yet, okay? We could also do this with a list comprehension. So I could say map f of x's is simply the list comprehension f of x for x and x's. This is almost Python code, actually. That would work, except what? Right? Why do you think we need a map that just, when we have this list comprehension? What did I just show you before this? Pardon me? After that lamp. We were just talking about what for like the last few slides? Iterators. What happens if an iterator is infinite? Can I put that in a list comprehension? No. Right? So these higher order functions are not just going to work over lists. They're going to work over iterators. Right? So I can say, create me an iterator that gives me all of the integers. One moment. What's up? Yeah, but then it's just going to go through it. It's going to then launch that for loop. Like I agree with you, the for loop is going to call the iterator, but it never stops, right? It's going to go on for infinity. Like the for loop doesn't hit next and wait. It calls next, then calls next, then calls next, and until it hits the end, right? If I put that in okay, let's try this. Oh, I can't do that because they won't see. How can I create an infinite iterator? So like when I do something like this, x for x in range 4, like it really expands that. Now, I don't know if I can put float inf in here. Let's see. Missed a thing. Okay. Can I convert that to an int? No. I'd have to build a custom one. But suppose I just built an iterator that just like went 0, 1, 2, 3, and so on. Right? It's trying to build, it's like the for loop is going to say, okay, I'm going to run through this iterator until the iterator exhausts. Right? Otherwise, because what is it? It's not going to wait at every iteration, like asking permission to go to the next iteration. Like, so if the for loop over a finite iterator, right, will eventually terminate, because then it will hit next, it will get the stop iteration. That's why it's called stop iteration. So otherwise, if I did map like this, and x's was an infinitely long iterator, you get an infinite loop. And you would occupy all of your memory, right? Because you'd be trying to build an infinite list. Okay, so what this map allows us to do actually is to like apply this notion over things that are infinite, right? So what do we expect map to return? An iterator, right? If I map some function over an iterator, it's going to give me back a new iterator, which basically says, well, call next from the stream, capture it, apply the function, and then return that as next, right? And you can keep recursing on, like this is the beauty of it, right? I can do a bunch of computations that does 0 computation until I actually like stream from the iterator. And that's sort of the point, okay? So all these higher order functions are typically reproducible in lists, and I'm going to show you what their definition is over lists. But the reason that they're here is because they more generically work over iterators. Okay, so let's see how this works. Okay, so I'm going to create a function called divisible by 3. Right? Remember, this is a weird statement, right? 6 mod 3 is 0, so that is divisible by 3, so I have to put a not over that, right? So again, this is testing for divisibility by 3. I can say map divisibility by 3 over the range 8. So this is the numbers 0 through 7. And what do I get? A stream. And now I can just sort of like ask for some members of these streams. And it's saying 0 is divisible by 3, 1 is not, 2 is not, 3 is. Right? But I can't go backwards. I could have also put this in to a list comprehension. Right? So I can always say, you can take any iterator that's finite and just do an integer casting over it. I can say, convert this iterator to a list and it will just sort of put it there for you, right? So this is useful in debugging, right? If you ever want to look at your iterators, but again, this is going to crash if your iterator is infinite. I can also say something like this to force the evaluation. I can use a list comprehension. So I can say x for x in this map, right? Spin up this list, and that's going to work as well, okay? But again, this is only going to work under the condition that your stream is finite, right? If the stream is infinite, that is, it doesn't provide a stop iteration condition, you're just going to get infinite loops. And worse than just an infinite loop, you're going to have an infinite loop that's slowly going to occupy all of your memory. Here's an alternative to map, right? So suppose now that we're like dealing with lists. And lists have to be finite. We have no concept of an infinite list in Python. That would be a stream. Okay, so it's very typical to see this rather than a map if you're actually like working over a list. So I can say divisibility, divisible by 3x for x in range 8, and that gives you something like that. Right? So for finite lists, you can do this. Here's how we could define, so I'm going to show you a recursive definition for all of these higher order functions over lists. I could have shown you them for iterators, but we're very new to recursion, so I thought I would just limit it to this space. If you want to see how everything else works, come join me in Comp 3400. But here's a new type called callable. Right? This just means f is a function. Right? You can call it. Right? You can give it input. So here's how we can define a map over f, and mapping that f over x's. So how do you map the empty list? Well, usually it's just the empty list back. Right? There's nothing to map. It's an empty basket of fruit. Okay? And then we want to return the f at the first element of this list. And then I want to put that, like make it a singleton list. And then I just want to concatenate the map of the rest. Right? That's how all of these functional patterns are going to be very recursive. Right? Everything in functional programming is done recursively. Everything. Right? You don't have loops. You don't have like reassignment. Right? So it's a totally different way of thinking. But it's nice. It's really elegant. Okay, so that's map. Any questions on map? Right, so given a list and a function, we now have a provision for applying that function to every individual element of a list. And in fact, more generally, we have a provision for applying a function to every individual element of anything that's an iterator. Zip. Zip is what you need if you want to take two lists and you sort of want to combine them somehow. Right? So given a list x's and a list y's, zip is going to give you back a list of tuples where the first element of the tuple is from the first list and the second element of the tuple is from the second list. Something like this, right? So, oops, wrong way. Zip of these two lists, 1, 2, 3, and 4, 5, 6, 7, is the list 1, 4, 2, 5, 3, 6. Notice that the zip truncated to the shorter list. And that's what it does in Python. So this is useful if you'd want to do something like have two lists and want to do sort of like their pairwise addition. Right? If you have two lists and I want a new list where the new list is members, just sort of the sum of all of them, this will become more clear in examples, but this is what zip does. Sometimes zip comes with another parameter called a function, and when that's the case, it's called zip with, but Python doesn't have zip with. Okay, so again, all of these high order functions I'm showing you have been defined to work over iterators, right? Range is an iterator. Right? You've ever tried to like look at range in Python and be like, it just says I'm a range. That's why, right? Because the range is iterating. It doesn't want to display itself because that would force an evaluation. Okay, so I'm giving two iterators. I have x's and y's. The first iterator is going to be what numbers? Just let's do a little practice for your exam. 1, 2, 3. Remember, left inclusive, right exclusive. Y's is going to be 4, 5, 6, 7. So I say z's is going to be the zip of x's and y's. So if I ask for z's, what is it going to show me? Yeah, it's just going to say I am an iterator, right, at this memory location. So I'm just going to take this iterator and convert it to a list just so I can see it, which we can do, right? Because how many of the lists here have to be finite for this list operation to work? One of them, right? Because we're going to truncate to the shorter list. So actually, one of these lists could have been infinite. Right? So here you go. 1, 4, 2, 5, 3, 6. Okay? The individual higher order functions aren't that difficult to understand. The nuance comes from combining them in a particular way to like make it do something that is useful. Here's a recursive definition for zip over lists. So suppose you've given me a list x's and a list y's. If either of the lists are empty, you're done. Just return empty. Otherwise, sort of give me the member, or give me the element at the front from both lists, make that a tuple, make that a singleton list, and then concat with the zip of the rest. Recursive. Simple. Lovely. Elegant. Okay, so zips aside. Filter. So a filter is used to either select or remove elements from a list. You've seen this already in this lecture. List comprehensions can have an if statement. That's effectively filtering. Okay, but that won't work on streams, right? So sort of this filter is the more generic version of just giving an if statement to a list comprehension. So it sort of works like this. Filter, given some p, some proposition, that is some univariate function that evaluates to either true or false, like greater than. You give it something iterable, and it says x for x in x is if px, right? That's the sort of equivalent in the list comprehension. So it's something like this. I can filter, and I can ask the question, is positive, right? So I'm saying filter as in keep the elements from this list that satisfy is positive. So if I run that, you're going to pull out 1, 2, and 3. Right? Those are the positive elements of that list. Of course, that's not how it works sort of in practice. So if I just generate a bunch of random numbers, so this is going to be 5 random numbers from -10 to 10. Here's x's. Right, so here are my random numbers. And then I can say filter, lambda x goes to x greater than 0. Sort of that's the realization of, is positive. Z's is going to say it's an iterator. All right, and then I can force evaluation and get, 4 and 2. Here are the positive numbers from that list. And I hope sort of light bulbs are going over your head saying, oh, I could have used this here. And this could have simplified my code in the following way. Because it could. When I was at the University of Toronto, actually, we did all of this like at the beginning, right? Just so if you wanted to, you could be using them. Here's how filter works over lists. So again, if I want to filter over an empty list, that's just empty. Otherwise, if it is true that px is not, so the thing currently at the front of the list triggers true, right? That means you want to keep it. So that's keeping it. This is just a clever way of saying, give me the first element of a list, but keep it as a list. It's the list slice from 0 to 1 exclusive. Right? So this is going to return a list with one element in it. That element is going to be x is not. And then I just want to concatenate, filter the rest. Right? This is sort of the rest of the list. Now you see why these list slices were created the way that they were. It makes recursion really easy, because I can say, give me the first element of the list and pass on the rest of the list. If it wasn't the case that the initial element of the list satisfies the proposition, then we just dump it. Right? Then we just keep filtering. Just drop this element and try the next one. So that's the simple recursive definition for filter. All. This is very useful. I'm sure you can find use cases for this. All checks if every member of a list satisfies some predicate. Right? So if you want to see if a bunch of conditions are true simultaneously, one way you can do it is to write a gigantic if statement. Another way of doing it is to use all. Right? So provided x is, well, in Python everything has a Boolean value. But you typically give all a list of Booleans, and all evaluates to this statement. Right? It just says It just puts an and in between all of the list elements and then evaluates that conjunction. So that's not Python code, but it is what it's doing. The problem becomes, what happens if this is an infinite stream? What happens when this is an infinite stream? Right. Okay, so what happens when this is an infinite stream? What happens if there is no false? So this is a category. So these topics are now really approaching computer science rather than software engineering. There's going to be this branch. Okay. So to ask if every member of a stream is true, is something called semi-computable. Why is it semi-computable? Well, if there's a false, I'm going to stop and report the correct answer, false. If there's never a false, I'm going to loop forever. Right? So what does looping forever mean? That means like I'm still looking for false. When is it going to be true? At the heat death of the universe. Right? So we're allowed to have sort of these semi-computable values. And we can talk about the space of things that are computable, semi-computable, and non-computable. Right? That's what you'll be learning more in computer science if you move up the ladder. Okay, so it is true that all of these things are true. And it is not true. Oh, that should be a false. That all of these things are true. Okay. Are all elements of X's positive? Right? This is sort of a use case of this. How do I do this? Well, I can say, are all, okay, I want to take my list. I want to map to it the isPositive function, which leaves me with a list of true and falses. And then I want to ask if all of those things are true. Right? So all sort of is not useful by itself. Like you really need all in conjunction with map. You have some list. You want to test for some property P. So you map that over the list, and then you ask if all of those things over that list are true. Right? So here you start seeing how these higher order functions start giving you a ton of functionality once you start mixing them. Individually, they're sort of easy to understand, but again, the nuances in combining them. So this is true. How can I ask if all of the names in this list start with a B? Right. Exactly the same line, but rather than x greater than 0, x at 0, check if x at 0 is the capital B. Right, but how would you have done this without these higher order functions? Right, you would have had to set up a for loop and then check every individual name and then have some type of escape return to throw false or for true. It certainly wouldn't be one line like this, right? Which can go in an if statement in your code, right? So I'm just going to say, do all the names start with B? Well, is it the case that all of the elements, when you map this lambda function, right? So C's to C's at naught is B, is false, right? Because this doesn't start with a B. Cool. I don't think we're supposed to use, I checked this last night. String comparisons are supposed to be done with equal, right? Is comparisons are just to be done against none. Like that's really like a memory location check. So if you're tempted to use is, you're probably not supposed to use it. So I can check again. I'm pretty sure though. String comparisons, Python. Okay. Yeah, equal and not equal. Don't use is. You're just tempted to use is, not you as in the general you, because it's easier to read when you're reading your, right? It's nice to say, oh, if x is 7, right? But that is something fundamentally different. So you use equal. Okay. Here's the recursive definition for all. Again, these are all like surprisingly simple. So this is a little bit troubling though. So what should all give on the empty list? right? So what's the question we're asking for all, right? Return true when what? I wouldn't say when everything is true. I would rather say when none of them are false, right? Again, it's easier to conceptualize checking for the breaking of the condition. So if you have an empty list, like, does it fail to, like, is any of the elements false? No, it doesn't have any elements. Okay, so thereby, all of the empty list should be true. Here's another way of thinking about this. The other strategy I gave you for recursive things was to ask, well, go one level up and see about that. So if I have the list and it has true in it, certainly all of the singleton list of true should be true, right? So what does that recursion mean? Okay, that would say, oh, that shouldn't be here. What is this? This is totally wrong. There's no callable here. So just ignore that. This should just be bool. Or, okay, geez. I'm just going to take this out and then put it in here. Huh? That shouldn't be here. I just want highlighting. That should be like this, essentially. Okay. So this is what I'm talking about. So we want to say all true, right? But all true is going to be equal to true and all empty. Okay? What happens if I make all empty false? Everything is false. Literally everything. Everything is going to eventually end false. Yes, miss? Yes? Oh, thank you. Okay, so by this logic, all empty can't be false, because it would just always return false no matter what we give it. Therefore, it has to be true, right? So that's a second way of understanding it. I prefer the first way, right? There are no falses in an empty list. Okay, we have all, and we also have any. So this is essentially equivalent to the predicate for math, there exists. So any is very similar to all, except that instead of throwing ands in here, we're throwing ors. Right, so this is going to answer the question x is not or x is 1 or x is 2 or to the last. So is it the case that any of these are true? Yeah. Is it the case that any of these are true? Yeah. Is it the case that any of these are true? No. Why? Because we can't find a true among them. Is any element of x is negative? How do I ask that question? Well, are any of map lambda x less than 0 to x is true? No. Does any name start with a C? Well, I'm going to map lambda C's to check if the initial thing is C's. Right, so that's going to turn this list into true, true, false, true. And then that should be an any, my lord. And then I'm going to ask if any of those are true. That's going to be this one, so that returns true. Right, and you can put you put these in if statements. You can say if all map lambda C, and once you get some practice reading these, the conditions that you're checking become very clear. So here's a recursive definition for any. I just swapped, and again, these have to disappear, these callables. I just swapped that and for an or, and I swapped that false, that true for a false. Why? Well, suppose the last thing we or is true. What does that mean? Everything is true, right? Because you or true. So that's why the last thing has to be false. Another way of thinking about this is that we're searching an empty list for true, and there is no trues in the empty list. There's nothing in the empty list. Here's an exercise for you to do. Define all and any using filter. Think about how you could do that. Folding. Okay. So this is the most sophisticated, higher order function that I'm going to show you. It's a little bit nuanced, and you may have to think about it a bit. But at the highest level, it basically means if you give me a list, and you give me some sort of, you know what a bivariate function is? Univariate means one variable. Bivariate means two variables. So things like addition and multiplication are bivariate functions because they take two inputs and return one input. Right? A plus B equals C. So if you give me a list of things, it may be the case that you want to like insert a bivariate function. Okay. So do you know the difference between infix and postfix notation? Maybe. So like plus, minus, times, divide, those are very, like, we don't normally call functions like that. You normally call a function f as, say, f and then give it something, right? When we use plus here, this is a notation for a function application. Which function application? This function application, right? 1 plus 2 is really a notation for give 1, 2 to the bivariate function plus. It's just notation, but it's important that you understand that there's infix and postfix, right? So this is the infix notation. This is the postfix notation. And obviously, infix notation is less messy, right? That's why we sort of introduced it. Okay. So you just have to imagine you have some list, and you want to like put some infix operator in between them, right? So I give you 1, 2, 3, and suppose I wanted to add them all, right? That would look something like this. But really, if we want to be consistent, all of the functions that we typically use are defined in the postfix notation. So it's really doing something like this, right? It's just making a recursively saying, keep applying this infix operator. Okay, so we'll take closer looks at this. Okay, so that process is generically called folding, and the higher order function in Python is called reduce. Right? So in order to fold, you call reduce. So here's how reduce works. So here's reduce. Here is some bivariate postfix function. Here is a list. And it does this. Right? So it's sort of like says, okay, call that function on the first member of the list, and then the second member of the list, and then use that as like the first input, right, to the thing with the next. Right? So it's easier to see this in the postfix notation, or sorry, the infix notation. So suppose that at, right, I'm just using this as a symbol. Right? Suppose you have some bivariate function, call it at, and let's call that at using the infix notation. Right? Reduce essentially does this, okay, infix. And this is what it does sort of postfix. So that's sort of the confusion here. Right? You have to be able to understand that you can like move in between postfix and infix. Right? They're just different types of notation. Okay, let's do some examples. Okay, so this offends me almost. Okay, reduce isn't included in Python. I don't know why. Right? Map is, filter is, all the previous higher order functions are standard. You have to call reduce from functools. Now, typically, I never import a function like this. Normally I would call functools.reduce. I believe reduce is so important that it should have been included in the first place. Right? So here's the one exception. I'm just going to just call in reduce. I'm going to say, give me this reduce function. So I'm going to say reduce this list using addition. It's going to give me 9, right? Because it just sort of said 2 plus 3 plus 4. And this is the way we can do this. Reduce isn't going to work over infinite lists because you need to stop and it needs to return something. I can multiply over these things, right? So this is going to say 2 times 3 times 4. Okay. Power. So here's a problem. Addition and multiplication are both associative operators. Do you know what it means to be associative? It means it doesn't matter how you bracket the expression. You're always going to get the same value back. Right? So you can bracket 2 times 3 times 4 in whatever manner you want. It doesn't matter. However, exponentiation, subtraction, division are not associative operators. It does matter how you bracket them. So what is this going to return? I'm doing 2 to the power of 3 to the power of 4, right? But depending how I bracket, you may get either 2 to the power of 3 to the power of 4 or 2 to the power of 3 to the power of 4. So which one is it? Well, let's just take a look. So it's going to be, so if I just put this into Python, it's going to say 4096. So 2 to the 3 to the 4 gives 4096. Okay? So this is going to be left associative, right? The brackets are stacked to the left. They're not stacked to the right, which would give this. Accordingly, folding actually breaks down into 2 subcategories: left folding and right folding. Left folding is when we do left associativity. Right folding is when we do right associativity. Reduce does a left fold, and there's not really a way to do a right fold in Python. Okay, so just keep that in mind, right? When you're reducing, if there's ambiguity in terms of association or associativity, it is left associativity. What should reduce do on empty or singleton lists? Well, that really depends on what function we're folding. Okay? And since it depends on what function we're folding, this needs to be an input to reduce. And I'll show you what I mean by that. The input to reduce is usually, but not always, what the identity or zero of the operation is. So that is to say, for addition, you want a base case where you can do exactly one more addition that's not going to affect anything. Right? So I can always add 0. Right? So 0 is going to be the base case for addition for reduce. When I'm multiplying, I can always do another multiplication by 1. Right? So that's going to be the base case for reduction over multiplication. For exponentiation, I can always take something to the exponent 1 without affecting it. Right? So that may be the base case for exponentiation. Yeah, exactly. Like this now is starting to sound a lot like math, like a lot like algebra or group theory. And in fact, you take Comp 3400, I'm going to show you exactly how we make this transition from algebra to functional programming and back. Here's a singleton list. So I want to be able to reduce over this. Or so what does it mean to like put pluses in between this? There's like you need at least 2 things for a bivariate function to work. So you can also give reduce an additional argument, right, an optional argument, to say if I don't have enough elements, like use this one. Right? So this reduction of addition over this singleton list is going to become 2 plus 0. I can say if you don't have enough elements, right, the default element is going to be 1 for multiplication. Right? So reduction over the singleton list 2 using multiplication will give you 2. I could say reduction over exponentiation. If you run out of things, just take it to the exponent 1. Right? So these are sort of the base case is just an invariant for the arithmetic or operator that you're doing. Now, what does this mean for the empty sets? Right? So this means that we've in fact said what it means to do an addition over the empty set or the empty list. So if I reduce the empty list, it's just going to return like that base. Right? So what does it mean to sum the empty list? Well, you get 0 back. What does it mean to take the product over the empty list? Well, you get 1 back. What does it mean to take the exponentiation over the empty list? Well, you get 1 back again. Right? And like Python implements this, right? So we should have, I think we have some. Right? That's why this is the case. We also have prod. Do we not have prod? Maybe it's mul. What's the version of product for sum? I'm sure it exists. Chat? I always forget. times? I don't think so. Now let's do a little bit of Googling. Some product for Python? I'd be very surprised if it didn't exist. Oh, okay. It's not there. Okay, so there is no, but you could easily build one now, right, using this reduce. Right, so I can do it now if you want. So I want there to be a prod. That needs to be a lambda function, which takes x's to reduce. And I want to reduce lambda x and y to x times y over x's with the base case 1. Right, so boom. All right, now, what? Oh, C, damn you. From func tools import reduce. Okay, so now I have my product operator. See? And like, look at this. This is such a nice statement, right? If we had to do this using our old techniques, we would need a function, a for loop, and returns. This is the kind of stuff that I love. Okay. Of course, you're not obligated to choose like a sensible base case, right? If I say, if you run out of numbers on this list, use 10, right? And this is going to be 10 plus 1 plus 2 plus 3. I can say, oh, okay, if you run out of numbers, use 0, which just means everything is going to be 0 here. Yeah. Logarithm is not a bivariate function, so you can't reduce it. You can only reduce things which take 2 inputs, right? Because remember, you just have to imagine it's an infix operator and you put it between stuff, right? So log is a univariate function. You can map it, but you can't sort of do a fold unless one of the inputs is the base, right? But then that would be quite a weird thing to be folding. Like you'd be taking the log of the first thing with the base as like the reduce of the rest. So. Well, identity, well, yeah, you can't do an identity because again, that's a univariate function, right? Right, so the plus operator here is going to be that of list concatenation. So I can say, like, reduce this list concatenation over this list, which I expect to give 1, 2, and 3. But this is a very illustrative example because 0 gets put at the front. Left folding, right? So the last thing will be used as the last thing to go left. All right, so you really have to play with these folds, and I really have to rush. Here's the definition of reduce over lists. You take a look at it. Here's some exercises for you to, well, okay, actually, let's just look at this. That's all you really need to understand. I'm taking the last thing of the list. It's sort of like backwards recursion. I'm saying, okay, take the last thing of the list and like make it the second thing, the second input to my bivariate function. For the first thing if that's my bivariate function, recurse, like do a reduce and repeat. So study this a bit. Okay, I want you to go home and define some product of integers using reduce. I already did one of them. You can do the other. I want you to define concatenate, which given a list of lists, return the concatenation of those lists using reduce. I've already sort of given you the answer for that. Define all using reduce and map, and define length using fold and map. And when I say define, I mean produce a one-line version, right? All of the bets go out the window if you start going and making a function, right? So in this functional programming, it is implied that you are writing one-line functions using lambda. Okay, next, sorting and complexity. We got to burn through it. So any questions before I go on to the next thing? Okay. Again, like this was supposed to be a 2-hour lecture. Okay, just a little drink of coffee. Okay, coffee, screen, spotlight, ensure, mute, record, warning, complexity and sorting. Sorting actually is not a part of this course, which surprised me. Sorting is like the most important problem in computer science, or at least it's like the canonical example of why we need computer science. So what we're going to do today in this lecture is create or look at 4 different ways of sorting a list. And then we want to ask the question, which of them are the best? which requires us to like talk about, well, what does it mean to be an efficient algorithm? Like beyond just timing it, which comes with its own sort of baggage. Okay? So really, we are now talking about the transition from software engineering to computer science. If you go interview at the Googles, the Twitters, the whatevers, at your interview, once you write your solution on the board, they are going to ask you, what is the complexity of your algorithm? Right? They're going to say, give us some measure of the effectiveness of the thing that you just wrote. All right, so this is something that you need to care about. And I'm just going to give you like the slightest sample of it today. Okay, so first we're doing sorting, then we're doing complexity. Was that a question? Yeah. Yes, that's what we're going to do right now. We're not doing space complexity though, this time complexity. Okay. Okay, so first let's talk about the sorting algorithms. Then we're going to talk about complexity, and then we're going to return to the sorting algorithms to deduce which one is the best. So the philosophy for these sorting algorithms is we're going to presume we can do one thing and then ask if using that one thing can sort a list. Okay? So suppose that the only thing that we could do, is this right? Okay. Suppose the only thing that we could do was given a sorted list, put something into that sorted list properly. Could we sort a list? You say no? No, I'm saying presume that. Presume we have a function that given a ordered list and a new element will return a new list which is sorted with that element in it. Yeah. Not really. Well, it's not, hold on. It's not a not really. You did exactly the thing that students do because it's easier, but it's actually going to make your life a lot harder, right? Not to pick on you, but like, why did you choose the singleton list? Because it seems obvious like what that should be sorted to, right? But it's also obvious what the empty list sorts to. So I'm just trying to like get this bad habit out right before it sort of like metastasizes. But you're right, essentially. But in any case, okay, so we have an empty list, and that's sorted. So I give you a new number, and you put it in, right? And that's sorted. Now what? You keep doing that. Okay. So here's a list. Like, suppose you have a list of unsorted elements. I'm just going to take the front of that list. I'm going to like take one member off and put it into a list of one. It's sorted. Then I'm going to take the next thing off of the list and insert, and it's sorted, right? So I'm just taking a member from the unsorted list and building a sorted list repeatedly, right? So yes, right, this is something called insertion sort. So let's look at how this insertion sort works out. I just need to go here and to create some bar. Okay. So let me just go and, okay, insert. Okay. So because we're short on time, I'm not really going to go through this. You can look, I'm going to post it, you can study it. It's tough. Well, it's not tough. It's just I hate working with indexes. It's very error prone. Right? You always like go one too much or one not enough. Right? So I'm sure you guys have the sophistication at this point to understand this. This doesn't use any higher order techniques. Right? It's just the most sort of rudimentary for loops in indexing. Okay? So here's an insert method that, given a sorted list, puts a new element into that list. But I had to do this in a little bit, I had to be a little bit smart about this, right? So the way that we're doing this is like, I don't want to keep duplicating the list, right? That's going to do more stuff than necessary. I want to sort of do the sorting like in place, right? So this is going to be given like the whole list, and I'm just sort of telling it like, pretend that like everything after K doesn't actually exist. right? So it's like, oh, I have a picture. I forgot about the picture. Here we go, right? So here's an unsorted list, okay? And as that gentleman said up there, its first element is a sorted list. So what I want to do now is like take from this list, like take this 26 and insert it into that ordered list. And you get this. And then I want to take this 93 and I want to insert it into this ordered list. And just keep repeating, right? And eventually the whole list is going to be sorted. Implement insertion sort. Okay, so I'm really running out of time, so I'm just going to show you. So provided you have this insert method, which I'll abstract away, like this is all you need to do for insertion sort. Right, so one comment here. If I didn't do this copy, the list that the user passes would have been modified. It is not. If I pass something to a function, I don't expect that thing I passed to change. Okay? If you want to make state-based changes to objects, you usually do that through a method, right? So there's going to be two ways of sorting, right? Like a sort that's called that's a property of the object itself, so like dot sort, or a function called sort, which then shouldn't destroy the object. So that's the sort of philosophy that you should have, right? Don't destroy user input. Right, so that's why I just did this copy at the beginning. Right? So I'm not touching the thing that the user passed. If the user really wanted to do an in-place sort, they should do that using methods. Right? Pardon me? Well, this is an integer list, so it doesn't matter. And also, how do you sort list of lists? You'd have to define an ordering on lists. Well, what comes first? The list 1 or the empty list? Because you're doing length? And anyways, you could do it, and I would need a deep copy. But remember, like the thing that you're sorting needs to form a partial ordering, right? So, and lists don't really have ordering, at least naturally. I think though you can't, yeah, they do sort of like, anyways, it's not a deep copy. In this case, we're just focusing on integers to keep things simple. But look how simple this is, right? I'm just saying, walk through the list, right? So, and just keep taking stuff from, like take x's of k and insert it into the first k parts of the list. Right? So it's essentially what the picture did. And again, sorry, I'm burning through this. You blame the government for moving ECA. Okay, suppose the only operation we could perform was swapping two adjacent cells. Could we sort a list? Yes. Pass through the list, right? So you just look at all pairs of your list, and you ask if those two things are ordered. And if they're not ordered, you swap them. And you just keep going through your list again and again and again until it's ordered. So the picture is really informative here. So I look at 54 and 26, and they're not ordered, so I swap them. And now I look at 54 and 93, and they're ordered, so I don't do anything. Then I look at 93 and 17, and they're not ordered, so I swap them. And then eventually, 93 gets to the top. This is called bubble sort because the largest value bubbles its way to the top. It rises to the top. Right? So, and then you just keep making passes over this. And eventually, one of your passes is going to trigger 0 swaps. And that's the condition where you conclude that your list is sorted. And so this is called bubble sort. You just keep going through. So implement bubble sort. So I can just show you where select. Here's bubble. Right, so you copy the list, and you just sort of perform that algorithm that I'm saying. Right, so here's the list swap right here. And you're going to have to go back and study them a little bit. But essentially, it's just an implementation of this picture. Right, and this is another sort of division between software engineering and computer science. This is an algorithm that you can implement well, you can implement poorly, you can implement in C, you can implement in Java, you can implement in Python, right? This is an idea. This is an instruction that is independent of any programming language. This is computer science, right? There are going to be computer science courses where you don't touch a computer because all we care about is the algorithm and not necessarily the realization of that algorithm within the computer. So you can look at that when you're home. Suppose the only operation we could perform, I actually missed one sorting algorithm here called selection. So I'm going to have to put that in. So there's one more question. Suppose all we could do is find the biggest member of a list. Could we sort a list? You could, yeah. So here's how this works. You give me an unsorted list, find the position of the largest member in the list, put it at the back. Find the second largest member of the list, put it at the second back. Find the next largest element. So you just keep finding the biggest element in the list, its index, and putting it at the back, and then decreasing the back by 1. I don't know why those slides got lost. I'll put them back. And I've implemented it into, it's here. It's called selection sort. Slides have gone missing. Okay. So suppose the only thing I could do was, given two lists that are sorted, combine them into a single sorted list. That's not too hard, right? So given two lists, you just say, who's smallest? I'll take you. Who's the next smallest? You just keep looking at the front of both lists and taking the smaller one to form your new list. Does that sort of make sense? Like how you could merge two lists? If that's all I could do was merge two lists, could I sort a list? Right, so I'm saying to you, here is a function that will merge two sorted lists. Sort a list. Sure. How? So you want me to split the list into its first component and its tail? And then sort the first one and sort the second one? Okay, you're like 80% of the way there. Why did you, okay, how about this way? Take your list, cut it in half. Isn't that should be a little bit better.
But like, what if the, like, say you've got 1, 2, 3 in the first list, 4, 5, 6.
Yeah.
Go 1 and then 4.
What? No, 1 and 4. You need to split the list into two pieces, right?
Yeah.
So what are your two pieces in 1, 2, 3, 4, 5, 6?
1, 2, 3.
And 4, 5, 6. Okay?
So when you merge them, you take the first one, right? And you check, oh, it's 1.
I don't care about merging. Merging is provided to us, right? I care about how to use merge to sort. And you're basically there. Okay, so consider this. Take your list, break it in half, merge sort the halves. Well, how do you merge sort the halves? Well, take that half, break it in half, merge sort the halves. Okay, but how do you merge sort the halves? Eventually, what happens? Well, eventually you hit size 1 or size 0, I'd say. And a list of size 1 is sorted already. And a list of size 0 is sorted already. Okay. So this is a recursive algorithm, obviously. So this is the winding stage of this merge sort. Take the list, break it in half. I don't care about odd size list. You pick where you want the extra one to go. Right? Break in half, break in half, break in half, break in half. Right? So this is like the base case now. Like all the lists sort of got down to like a single element. And then it starts unwinding, right? Producing sorted lists which get merged. Merge, right? So break everything up like this in its winding phase, and then start bringing everything back together. We're using merges in its unwinding phase. Now, I want to show you how this one works, because it's kind of nice. So I just need to take, okay, should we do everything? I think I'm running out of time. Okay, so I'm just going to take merge, and we'll consider that abstracted. And you can take a look at it later. So again, given two sorted lists, I'm going to return the sort of like their concatenation. So let's just get rid of this. Whoops. And let's define merge sort. Oh, come on. Stupid folding. Okay, merge sort. Given a list of integers, we want to return a list of integers. So how is this going to work? Well, if not x's, then return this. If length of x's is equal to 1, return x's. Okay, but actually, I can combine these two conditions. I can say, if this is less than or equal to 1, just return x's. So this forms the base case. Now I want to break x's in half. So how can I get half of x's? Oops. Yeah, from the start to half the length of x's. And then same thing starting from half the length of x's. No, I think the exclusions save us here. Which is why we provisioned right endpoint exclusivity. Okay, so that breaks the list in half. And then I just want to return the merge of merge sort on y's and merge sort on x's. And believe it or not, this should work already. So let me just get into bar. Let's just, I don't know, oh, shoot. I made a mistake. Where is my mistake? There's usually not able to be mistakes and stuff that's so simple. Z's. Not Y's. There you go. All right, look at this. Sort of list. Super easy. Yeah.
Merge sort method, is that almost an application of graph theory or binary trees?
In that, it's a divide and conquer strategy. So this is a very typical strategy in computer science. And I'm going to show you why it's super important, because it turns out that this merge sort is way, way, way faster than any of the other ones that I've shown you, in addition to being much, much easier to implement. Okay. So I don't know why selection disappeared. I'll put it back in. But which sorting algorithm is best overall? Like at this level, how could we answer? I kind of I just told you, but well, two answers to that. Like, yeah, like it's hard to explain this without first showing you what I want to show you about complexity. Like, different sorting algorithms are best on different types of lists, right? So bubble sort actually works pretty good if the lists are small, right? Bubble sort is also the best list sort to use if your list is already sorted. But that sometimes you're given a list that's sorted, right? And it's expensive to check if the list is sorted. So bubble sort of does both. Like there are other conditions, like what if your list is like mostly sorted? Like what algorithm is best for that, right? So, and there are multiple algorithms for things because we figure out better ways of doing things, right? Like at one point, insertion sort is like all we had until someone had to figure this out, right? Like in fact, the best sorting method, the typical one is quicksort, which is a little bit different than merge sort. But you will be studying many ways of doing the same thing, because it's hard to, like, what is the generic, like suppose we wanted to go time this. What list should we choose? Random lists? That seems sensible, right? But then all of our experimental results are saying, which of these algorithms is the best one for sorting random lists? Right? And there may be other types of cases that we care about. But again, this is precisely why I need to show you the things I'm showing you now, because we need some standard way of comparing different algorithms. Because it's at this point, it's not really obvious which one is best. So we could do some timings, which I will. But rather than timing them, like which comes with a lot of baggage, right? If you just say time how long this takes, for one, your operating system may schedule you away, right? Like I don't want to include in my timing, like when my computer put me on pause and checked email, right? So you first need a computer which was like super locked down to get accurate timing results. And, you know, if you time it on your computer, you're going to get different results than I time on my computer. And I'm going to get different timings depending on like what's happening on my computer with timing. So rather than timing, I'd rather look at my algorithm and count the number of operations that it's doing and say like, okay, like my timing is going to be proportional to the amount of operations that I'm doing, right? It depends like how fast your computer can like do one of these operations. For sorting, which are the operations that we should count? We're needing to count everything. There's usually something fundamental to the algorithm. So what are the operations that are fundamental to sorting? Well, if you're sorting a list, what one thing must you do? Pardon me? Comparing, right? That's one thing we care about, right? A sorting algorithm that does the minimum amount of comparisons is going to be faster. And what's the other thing that we do aside from comparing? What did I say, actually? Swapping, right? Like actually permuting two positions, right? It's something you're going to have to do when you're reorganizing a list. So if we look at all of our sorting algorithms and count these two things, like the number of swaps and the number of comparisons, your timings are always going to be proportional to that count. And actually, I just care about their proportionality. Like I don't care that it takes 10 seconds to sort a list of 100. Like what I want to know is, supposing that it costs 100 seconds to sort a list of length 100, how much will it cost me to sort a list of 1,000? Right? That's just a question about proportionality. I don't really care about the timing. I want to know, do I expect to wait twice as long to sort a list that's twice as long? Or do I expect to wait 4 times as long to sort a list that's twice as long? These are the types of questions that complexities are going to answer. So we measure the complexity of an algorithm, which is a value that's proportional to the runtime of the algorithm, by counting the number of operations performed. The number of operations is proportional to the length of the input somehow. Right? So it has to be proportional to something. For list sorting, it's clear, the length of the list. For other algorithms, it may be less clear, right, what the size should be measured. But sorting, it's clear. It's really this proportion that we care about, and the complexity is the mathematical notation that is required for communicating like what proportion the complexity is. Here's a algorithm which is said to have linear complexity. That is to say that if you double the length of the input, your runtime is expected to double. Right? You're in linear proportionality. Oh, that's weird. So here's how we're gonna count the operations done here. Right? So I'm gonna give a list called L, and then the list has length n. So this is going to cost, how many assignments are we going to do at line 2? 1. Right? How many assignments are we going to do at line 3? Well, 1. How many comparisons are we going to do at line 4? N. Right? Because I need to, this is pushing that index up, right? This is going to, this while loop is going to execute itself n times. Therefore, it's going to do n many comparisons. And it's going to do n many increments of index. So we've done 2n many operations plus 2 operations, right? So we've done n plus 2 many assignments and n many comparisons. So the precise number of operations that this does is 2n plus 2. But we don't really care about anything else but the lead term here. Have you guys taken calculus? Have you guys done limits? What's the limit of 2x squared as x goes to infinity? What's the limit of 7x squared as x goes to infinity? So we don't care about the constants, right? Both things are going to infinity. So this is why this is sometimes called the asymptotic complexity. We're comparing these algorithms as their input approach infinite size. And when the input approaches infinite size, constants and coefficients don't matter. Right? So when I count something and it's like 2n plus 2, I'm just saying that's just, it's in the same category of all the linear functions. Right? This, you can read this as big O of n is sort of like the set of all linear functions, and I'm saying 2n plus 2 is included in that set. Right? More formally, this should be an element of, but the notation is somewhat abused, and we use equal. Right? So this just says this linear algorithm is proportional linearly. Right? The expected wait time is going to increase linearly as your input scales. Right? So that means if you double the input, you wait twice as long. This is the precise statement for that big O notation, which you do not have to understand. But I'm just going to give it to you anyways. These statements look really complicated, but they're not. It's just because I'm using like fancy notation. We say that f of n is big O of g of n. That is to say the runtime complexity of f of n is proportional to g of n. And we write f of n is equal to big O of g of n when the following is true. When there is some constant c and some real positive constant k, such that for every n larger than k, f of n is positive and less than or equal to c times g of n. Okay. All this means is that if fn is a curve and gn is a curve, that cg of n is eventually always larger than f of n. Right? If you think about the parabola and the line is actually bigger than the parabola on the domain 0 to 1. Right? 1/2 squared is a quarter. Right? So you would be like the line goes like this and the parabola goes underneath it. But the parabola is eventually bigger than the line everywhere. Right? So that's what the k is. K is saying at what point does the one line always exceed the other. And C is just saying you're allowed to multiply by constants. So here's two examples. Like 2x squared plus x plus 1 is of the order n squared. Because eventually 3x squared is always larger than 2x squared plus x plus 1. Right? Namely, when x is greater than 2. X cubed minus sine x is order n cubed. Right? Because x cubed minus sine x is always less than or equal to x cubed plus 1, right? This is bounded by 1. Well, plus 1 minus 1. So if I just put a plus 1 here, right, that equality or inequality is guaranteed. And all of this is less than 2x cubed, right? So again, it's just like saying, who cares about constants and coefficients? Like, they are meaningless at infinity, right? So you got to think of these as limits, right? What is the complexity of this function? So you're given a list L. It has length n, and I'm going to spin up another index, and then both of these indexes are going to walk to the length of the list. So let's count. How many times, how many contributions, how many assignments does this do? How many assignments at line 3? How many times do we do a comparison? How many times do we do this assignment? How many times do we do this comparison? We do a comparison here n times, and we repeat that n times. So you're correct, n squared. Same thing for here, and this repeats n times. So 1, n squared, n. You sum them all up. So this does 2n squared plus 3n plus 1, which is in the order of n squared. Right? Because again, I don't care about lower order terms, coefficients, or constants. So quadratic means, okay, so again, we just care about the result on runtime. So if your algorithm is quadratic, that means if you double the input, how much longer do you expect to wait? 4 times longer, because we go with the square of the input. So what's going to finish faster, a linear algorithm or a quadratic algorithm? Most of the time, asymptotically. I'm not saying it's always going to be faster, right? I'm saying it's going to be faster, like maybe on average, or at least in the case of the largest input that you can give it. This is a little bit more tricky, right? What is to sort of really pin down what algorithm is better than another algorithm. N is equal to the length of the list. Index is equal to 0. Weil walks to 10 to the power of 10. That's like a huge number. Okay? How many assignments? How many assignments? How many comparisons? How many assignments? N? How many comparisons are we doing here? Wrong, right? How can we do n comparisons? N isn't included in the while loop. 10 to the 10. And so how many assignments do we do here? 10 to the 10. So if I add them all up, how many assignments, how many things am I doing? I'm doing 2 times 10 to the 10 plus 2, which is O of 1, right? This is a constant number of operations I'm doing. It's an enormous constant number of operations, but it is constant nonetheless. Think of it this way. If I give this a list of length 1, how long is it going to take? Well, say it's fixed. If I then double the length of the input, how long is it going to take? Well, the same, right? This algorithm is not affected by its input. Thereby, it has constant complexity. So here's the problem, right? This is constant time complexity. This is the fastest complexity that you can be. But our quadratic algorithms may be faster than this on smaller input, because complexity is only telling you that eventually this is going to be better than all quadratic algorithms. Eventually, right? But there may be some domain where it's not, right? So again, this is like asymptotic complexity. So anything that does a finite number, if anything that does a fixed number of iterations is constant. So if I try to trick you on your exam, right, by putting some ludicrously huge number in and asking you to compute its complexity, I may even have included some red herrings to distract you. If it's a fixed number of operations, right, it's just going to be O of 1. Yes? The 10 to the 10 is a number, right? So I could have said while I is less than 7. Right? And then it's just going to do 7 iterations every time. Again, that loop is not going to do anything different depending on its input. Right? What this while loop does is totally invariant to the input. The input doesn't do anything in here, actually. It's just a red herring. So fixed number of operations. 5 minutes. Oh, God. Yeah, speed run. Okay. What is the complexity of foo here? I have an input length n, and I'm doubling the index each time. Right? I'm doing 2 to the power of index. Pardon me? No. Well, okay. Yes. Because it's bounded by n. It's also bounded by n squared. It's also bounded by n cubed, and n fourth, and n fifth. Right? Remember, this is an upper bound, these complexities. So it is true that this has complexity O of n, but that's not the sharpest bound. 3 is bounded by 100, but it's also bounded by 50. It's also bounded by 4. 4 is the sharpest bound of 3, right? Right. So we're talking about when is one curve eventually bigger than another. You can always pick something big, right? So this is one of the things we do in computer science. Try to make these balances when we do a complexity analysis, it may be hard. We may get something very, we may get a bound, but it may be bad. We're always struggling to get the sharpest bound, right? So this is bounded by n, but there is a sharper bound. How many iterations how many comparisons at line 4 do I really do? How many times can I double the index? Or how many times can I? It's log base 2. You went the wrong way, right? Right, so this is going to do log of n many operations. Well, how many times can you double something until you hit that something, right? Log base 2 of something. How many times can I double 1 before I hit x, right? Log base 2 of x. And so you're going to have to go home and think about this a little bit, but I'm showing you this because for any divide and conquer algorithm, you are going to produce these types of logs. That's the point. Yeah. Yeah, you can just, sort of solve for this, right? You take log base 2 of both sides, and then you get index is equal to log base 2 of n, right? So that's not a bad way of thinking about it. Okay, sorry, I'm burning through this. Find the complexity of each of the sorting algorithms. So let's think about this. Insertion sort. How many times are we going to insert? N times. How much does an insertion cost? No. Well, in any measure you want. How many operations do we need to insert something into a sorted list? No, surely not one. What if it's the fourth thing? You need to do at least 4 comparisons. N, right? At most, right? At most, you have to do n comparisons to put an element into a list of length n, right? So if I need to do n inserts, what is the complexity of the insert sort? N squared. I'm doing n many insertions. I'm doing n many things that cost n. So that's O of n squared. Selection. What's the complexity of finding the largest element of a list? N. Right? At worst, you have to do to traverse the whole list. How many times do I have to do a selection to sort a list? No. The algorithm is selection sort, right? N, because every element has to be selected at least once to be sorted. So I'm doing n selections n many times, n squared. Okay, so insertion and selection seem to be equivalent. In the interest of time, bubble sort is also n squared. You can think about this at home. What is merge sort? How much does it cost to merge 2 lists? N, supposing n is the length of the bigger list. How many merges do I do? How many times can I split the list in half? Log base 2 of n many splits, right? But this is critically important. Insertion, bubble, selection are O of n squared, right? If you double the length of the list, you should expect to wait 4 times longer. That's pretty significant. Merge sort, n log n, basically linear. Log is like an incredibly, that basically erases any number that you give it. Right? Log base 10 of 1,000,000 is 6. 6! You just count the number of digits. Right? So n log n is like basically linear. Right? Just a little bit not linear. Okay, so there is going to be massive speed up. Right? Because if I double the length of the list to merge sort, I expect to wait twice as long, not 4 times as long. Slightly more than twice as long, very slightly. Okay, but here's the thing, right? So, because we could have borked our implementations of any of these algorithms when timing. If I would have designed insert or selection in a dumb way where I'm doing a lot of copying, like these lines would be different. Like maybe I did bubble sort wrong, because all the yellow, red, and blue all have the same complexity, right? But when I time them, they're different. So, but they all sort of have this like they all look like parabolas, right? That's the point. They're all proportional to the square of their input. This is the green thing down there is merge sort, right? Right. So, bubble took about for a list of length 15,000 over 200 seconds. I did it 10 times, right? So to bubble sort, to sort 10 different lists of length 15,000 took 200 seconds. Merge sort, to sort 10 lists of length 15,000 took 0.6 seconds. 0.6. Okay? So does this answer your question of why we need more than one sorting algorithm? Right? Well, yeah. And this is the point of computer science. I don't care that you can implement something, right? Most of you can implement insertion sort. Who cares? We need people who are able to figure out better algorithms, right? Which may not, like you may not even need to touch the computer to do that, right? So there are 2 paths that you're going to have to consider walking down. And one of them, I encourage you to, is my path, right? Let's care about the algorithms. Let's create better algorithms. Okay. Here's a little slide about how to time. I deeply regret that we couldn't go over this. I promise you to give you a solution. I'll post it online, but maybe I'll give you a hint so you guys can. Did anyone attempt this or do it? Okay, because this is a really nice exercise to like utilize all of the higher order functions that I gave you. Because there's lots of lists of things that you have to do. Here's a hint. Okay, create an algorithm that, given a list of tiles, can tile, and it's going to put something in its top left corner, and you tell it what to put there. And then all I have to do is like two flips. Right? So this is how you do a recursive call to get these 4 boards, and then you just do some flips. Right? A horizontal flip and a vertical flip. And you recurse on that idea. Okay? Okay, before you move, we're done. Thank you for showing up and for your attention. It really does make a difference to have people in front of me nodding along. Good luck on your exam. I'll be around to help you guys whenever you need. Festina lente. Any of you speak Latin? I want you to have this philosophy when writing your exam and doing any coursework. This is a Latin, and it means hurry slowly. Really, it does. Okay? I want you to like think before doing things, right? Ideally, try to read the whole exam before you start, and don't rush, right? It's going to take you longer if you rush. You'll make mistakes. So think and then do. Festina lente. That's the advice that I leave you with. Hopefully, I'll see some of you in future years. Best of luck. Hopefully not in this course again. Thank you, chat. That goes to you as well for showing up. I appreciate your input as well, and good luck to you. Thank you, thank you. You guys are great too. I'll talk to you later. Come visit.